Hi. Today we're going to wrap up a few loose ends that you probably have been finding when you experiment with your networks, which is basically a set of problems to optimize our network. And here, by optimization, I'm using the term in a loose sense that will include not only the optimizers themselves, so the algorithms that we use to minimize the loss function and optimize our parameters, but also hyperparameters that we have to decide. So the basic difference here is that the parameters in our model are learned through this optimization process of minimizing the loss function. But then there are other parameters that we have to choose. For example, how many layers, how many neurons per layers, what is the learning rate, and so on. So today, in this first hour, we're going to talk about a few of those problems and how we can try to solve them and improve the results we obtain from our network. So I'm going to talk a bit about different optimizers, how to choose the learning rate that we use, and eventually other hyperparameters that we have in the optimizers, methods for initializing our weights, or the first point where we start in the optimization to adjust the parameters of our model, and then a few things about how to select the model, the architecture of our network, the problems of overfitting, and regularization methods that we can use in artificial neural networks. So first, let's start with the optimization in this stricter sense of minimizing the loss function. So we saw this problem a few weeks ago. We want to minimize a loss function. We generally will obtain our loss function by this cross entropy, minimizing cross entropy, although the actual function itself will depend on precisely what we are outputting from the network, what our target values are, and so on. But we have this loss function that for which we can compute the derivatives with respect to all our parameters in this vector theta. And now we want to obtain the best values for those parameters given some data. Now, the details and the mathematics of the numerical optimization itself is outside the scope of this course. So even in the deep learning textbook that you have, you'll see a lot more detail than I will cover here. But for a more practical approach, it's useful to have some understanding of how the optimizers work and how they differ, so that when you are experimenting what works best with your particular problem, you can understand what's happening and what you're doing. So what we saw so far is stochastic gradient descent. So basically we have a gradient descent algorithm that tries to estimate the gradient at some point, or averages the gradient for a mini batch of examples. We've been using it that way. And then we'll update the parameters of our model so that we slide down the gradient surface. This means that at each step we're going a bit down on the loss function and we decrease the value of the loss function. So we've been using this class SGD from TensorFlow optimizers, but actually at present with TensorFlow 2, Keras is now so much integrated into TensorFlow that the optimizers are the ones from Keras. So if you check out what this class here is, it's actually just an alias for the SGD class in the optimizers module of Keras. So since today we're going to start using Keras, I'm going to use explicitly the classes of the optimizers from Keras from now on. But this stochastic gradient descent we saw is stochastic because it estimates the gradient given a random sample of the data, so usually a mini batch, although we can also use it with one example at a time. And then you can also include momentum. So in general, you should use momentum because it makes quite a big difference in how fast you can minimize the loss function. So this is what we saw so far. We saw a few weeks ago the comparison between the different ways of using this, without momentum, with momentum. Nester of momentum you can also use. It doesn't seem to make much difference in general, but you can also experiment with that. But this is not the only optimizer that we have. One particular problem with this optimizer is that it uses the same learning rate for all the different parameters. And this may not be a good idea, because if you imagine when you compute the gradient, for some directions, the surface of your loss function may be steep. And so in those directions, you can go very far. But in other dimensions, for other different parameters, the gradient may not be steep. There may not be a very big inclination on the loss function, and so these parameters will learn very little at each time step. So they will improve very slowly. This ADNE with adaptive gradients, this optimizer keeps the sum of the squared gradients for all the parameters. So at each evaluation, it computes the square of the gradient matrix and stores it so that it knows the sum of the previous gradients found for all different parameters. And the learning rate is divided by this sum for each parameter. So if you have parameters that are in a direction where the loss function is very steep, their gradients will be large, and so the learning rate that is going to be used will be smaller for those parameters. On the other hand, if you have parameters for which correspond to directions in which the loss function is very shallow and it's very level, horizontal, then those gradients will be very small and the learning rate will be increased. This makes it so that ADNE will try to optimize overall the parameters, even though some have very small gradients. Another aspect of this is that since it's keeping the sum of the squared gradients so far, so it's adding the square of the gradients for all the iterations, the learning rate will tend to shrink along the learning process, which is a good thing if we have a convex problem. So a convex problem is one where you have a sort of a bowl-shaped surface and you start sliding towards the bottom, and the bottom becomes narrower and narrower as you approach. So the bowl where you are it shrinks as you approach the bottom. So it's a good idea to gradually reduce the learning rate as you approach the bottom, because then you have a smaller chance of overshooting the bottom and missing the optimum point. So for convex problems, ADNE is good because of that feature. However, it's often the case that we are using neural networks for problems that are not convex. So they have strange shapes, and it may not be a good idea to keep shrinking the learning rate in this way. So there is this alternative, rmsprop. This is actually a very famous optimization algorithm for never having been officially published. So it was mentioned in some lectures and so on by the author, but then everyone started to use it, and it works well, especially in recurrent neural networks where the optimization is not tends not to be convex. It's usually a non-convex problem, and also with problems of convergence and so on. And the difference between rmsprop and ADNE is that rmsprop keeps a moving average of the gradient. So specifically, it's the root of the mean of the squared gradients, and that's why it's RMS this way. But this is not the sum over all the gradients met so far. It's an average of the more recent ones. So it keeps changing as you go through the landscape, the surface of the loss function, and does not accumulate as with ADNE. So this means that it will be kept up to date, and on average, it will not shrink the learning as ADNE does. It's also a bit different in that what rmsprop does is to divide the gradient obtained overall for all the different directions, so for all the different parameters, by this moving root mean square of the previous gradient. This means that we'll tend to level out differences in the gradients for different parameters, and they will tend to end up similar for all parameters. So it does something similar to ADNE in that it prevents the step in the optimization to focus only on those parameters that have a large gradient and ignore the ones that have a small gradient. So by evening out all these gradients using this moving average, it will tend to move along even those directions where the loss function is more horizontal and the gradient is smaller. So basically, the big differences between ADNE and rmsprop is in how they deal with the previous gradients found. With ADNE, it keeps adding them up, so the learning rate tends to shrink, which is good when you have a nice bottom where you have the optimum value, and you should go slower as you approach the bottom so as not to overshoot it. With rmsprop, the learning rate is not shrinking, and so it's good when you don't have this nice convex function to optimize, and you need to keep rolling, to keep moving along, and avoid getting bogged down and slowing down. There is another one that is very widely used, which is ADAM, that uses momentum. The momentum itself is also adaptive and uses an exponentially decaying average of the previous gradients to adjust the different learning rates. So it tends to be faster than rmsprop or ADNE, and usually it's the first choice. So in general, when you start learning something, you can try ADAM because it tends to be really faster than all the others. There is, however, one small problem. Sometimes it does not converge properly. So basically, if you try to step too far when you're doing optimization, it may happen that you miss the optimum values and you get derailed from the path. So ADAM has a larger chance of doing that, and you can start by experimenting with ADAM, but then be careful. Look at how the training loss is progressing and how far you can go, how far down the loss function you can go with ADAM to check if it's not one of these convergence problems. So basically, you have several optimizers to choose from. There are actually more optimizers available in Keras. You can write your own, so if you want, you can experiment with optimizers, but for this would completely leave the scope of this course. For our purpose here, the idea is that there is no real theoretical recipe that we can use to choose an optimizer. Basically, you must experiment and try to see which one seems to work better for your particular problem, taking into account not only how long it takes to train the network, but also how good the results are in the end. So be careful that if you're not getting a good convergence, even if it's fast, you may compromise the quality of the results in the end. So basically, this is one thing that you probably need to experiment a bit with when you're training deep models, is which optimizer to use and what parameters to give the optimizer. So in general, these rmsprop and ADAM and so on, they have some additional parameters that's usually not a good idea to change. You should use the default because it may be very sensitive to those parameters. But there are other parameters that you generally have to adjust. And the main one is the learning rate. So basically, if you have a learning rate that is higher, at each optimization step, you're giving a larger step. You're adjusting your weights more. If your learning rate is smaller, then you're adjusting your weights by smaller steps, by smaller increments. One advantage of having a large learning rate is that you can have a very steep learning curve, so you learn very fast and you reduce the error very quickly in the beginning. So you see, after 250 epochs, we already are here. One disadvantage of having a large learning rate is that then you may start to overshoot the optimum point, and so you start increasing the error again. So instead of having a nice smooth curve going down the value of the loss function, you have these hiccups here, all these jumps, because the step for the optimization was too large and you passed over the optimum point, and now you are in a worse position than you were before. So if this happens, you know that the training rate, the learning rate is too large. So you should reduce it and try to get something that is smoother And the ideal would be to try to get as fast as possible this descent on the loss function without having this kind of oscillations of convergence problems in the end. So this may take some experimenting and adjusting and training for sometimes to see what is best for each problem, because this depends on a lot of features such as the actual problem you're solving, how many layers you have, the network, and so on. So usually you will have to experiment a bit with the learning rate. There are some more sophisticated approaches, and you can use that. We're going to see some examples. It's easy to do in Keras, where you can start with the learning rate and then decay the learning rate so that it will reduce as you progress during training. So it would be good for things like this, where you take advantage of a large learning rate in the beginning, but then you start reducing the learning rate so that you don't have these oscillations, and you keep things smoother. You can do that, but this would be an additional parameter to experiment. So remember, the more flexibility you have, the more things you have to fine-tune until you get it right. So we're not going to focus too much on this, but I'm going to show you how to do that with Keras, where you can just set a parameter there. And today you're going to experiment a bit with these things to get a feeling for how it works. Another issue that we found, in fact, we had you saw a small example of a problem with this, where you had all those not a number values because of the initialization of our network. So there are basically two different things pulling in different directions here. One is that we must randomize the weights for our neurons, because we need to break symmetry. If two neurons on the same layer have exactly the same weights, then all their derivatives will be the same, and they will always be trained in step. So they will never diverge and be different one from the other. So we need to avoid having those cases. We need to avoid having neurons that are exactly the same, and so we must randomize the weights. We don't need to worry too much about the bias, so that particular weight that always multiplies by 1, because this is basically just a way to center the response of our neurons. We can start this at 0. We can use some heuristic, because depending on the problem, there may be some better values to start the bias neurons, but these are not particularly problematic. The ones that are problematic are the weights that are multiplied by the inputs, because on one hand they must break symmetry, and we must have different sets of weights for different neurons, but they also keep multiplying. So as if you have a layer with 100 neurons, then each neuron will multiply its own weights to the input, and then a neuron that is on the next layer will receive inputs from these 100 initial neurons. If we have activation functions like rectified linear unit or something like that, which are not bound in some upper value, then this may cause stability problems in our network. Even if the activation function is bound, it may saturate quickly, and then you have something, for example, the sigmoid activation. As it approaches 1, the derivative drops to 0. So it's a problem if you have large networks and the weights add up to a large number, and then everything stops working properly. So typically, initialization involves selecting random numbers that come from a range that depends on these values. How many inputs you have into the layer. This is usually called the fan-in parameter. It's the fan, the size of the fan that is coming into the layer, and how many outputs you have in the layer. So this is the fan-out parameter. So basically, fan-in, if you are stacking layers in a multi-layer perceptron, basically fan-in is the number of neurons in the previous layer, fan-out is the number of neurons in the layer that you're considering. And these usually are the parameters where we're going to find the limits for the distributions to initialize the weight. For example, this LeCun normal initializer initializes the weights drawing from a normal distribution that has a mean of 0, so it's negative or positive numbers, and the standard deviation is the square root of 1 over the number of inputs coming into the layer. And this is one heuristic way of selecting values for initializing the weights. Another widely used initialization is normalized initialization, also called Glorot uniform initialization. So in Keras you can use it with this keyword, and this is actually the default initialization scheme in Keras for dense layers. So those for multi-layer perceptrons like we've been using so far. And this is takes each weight drawing from a uniform distribution that has these limits, minus this square root and plus the square root, so it's between these two limits, and the limit is the square root of 6 divided by the sum of the inputs into the layer and the number of neurons in the layer. So this is not something that is a very solid theoretical result, but you can see here these kinds of heuristics that try to find a compromise between breaking symmetry and having a large diversity of values so that neurons are different, but also trying to avoid having too large values that may break down anything. This sometimes, if you have very large networks, it may also be a problem if you start shrinking too much this and the weights start all very close to 0. So if you see the textbook, there is some discussion about that. But basically, for the kind of problems we're going to handle here, we can leave the default most of the time. If you want to experiment, you can try to check out the different initializers that you have in Keras documentation, and it's easy just to experiment the different ones. So you have the formulas there and what they're doing. The basic idea is to understand the two things that we're doing here. Breaking symmetry, so giving initial weights that are different for different neurons, but also trying to avoid having very large values when we add up all these activations. So we need to start with the weights close to 0 and closer to 0 if our networks are very big. Okay, another trick that we can do to improve learning is to standardize our data. So basically, what we do when we present data to the network, we try to center everything. So we subtract the mean value and then we divide by the standard deviation so that the dispersion over all the different dimensions is the same, is one standard deviation for whatever dimension we're considering. And this is ideal because now we are using all the different features have an approximately normal distribution centered at 0 and with one standard deviation, and it helps the network. However, when we have a deep neural network, we have stacks of layers, and each layer is not seeing the input values that we standardize, but it's seeing the output of the previous layer. And this output during training may change quite a lot. So each layer is trying to learn as a function of the previous layer, but the previous layer keeps changing. And this makes training a bit harder, not only the variations, but also the change over time. Batch normalization tries to solve this or mitigates this problem, and it's actually a very good technique to improve training in the network by standardizing the activations of the previous layer. So basically, during training, we are computing the average and standard deviations of all the outputs of the previous layer. So what is input to each layer, and then we use those running averages to standardize the outputs of the previous layer. So just like we do for the inputs of the network, we are also doing for hidden layers too. And this eliminates these shifts in mean and variance during training, because then each layer of our deep neural network is always seeing a set of inputs from the previous layer that has a means of 0 and a standard deviation of 1. So everything is centered and only the shape is changing. And this also reduces the need for each layer to constantly adapt to differences, to changes in the previous layer that occurred during training. This is very easy to do in Keras because actually batch normalization works like it was an intermediate layer between the two of them. You can just stack a batch normalization layer, because all of these operations, computing the running average, dividing by the standard deviation, subtracting the mean, and so on, all of these can be taken into account by autodiff, so all the derivatives can be computed, and it works just like an additional layer in backpropagation. You can backpropagate through these operations. So in fact, with carriage, it's very easily. You just keep stacking. You put, for example, a dense layer, and then you can put a batch normalization layer, and so on, and you can use these in a very practical way. And this can greatly speed up the training of the network by keeping this standardization of the different layers. Now, another problem that we're going to have is the problem of overfitting. Usually we want to train a model, a deep learning model, to adjust to a set of data that we know, but so that we can use the result there, the hypothesis that we obtain, to make some predictions about new data. So this is the basic idea. We want to do predictions outside the data that we already know. Otherwise, it wouldn't be very useful if we could only predict what we already know. So the problem of overfitting is that we adjust too much to the training data and then make lots of mistakes outside the training data. And there are basically two ways we can solve this. We can minimize or mitigate overfitting by choosing models that don't overfit so well. So this is basically model selection. We can change the architecture of our network, different networks, and so on. And another approach is to use regularization. Regularization is some adjustment to the training process that doesn't change the model itself, but it can constrain or bias the way the model is training so that it doesn't overfit so much. So, and we're going to look at these two approaches here very briefly, because this is a common problem with machine learning in general and with deep learning in particular. So how do we check for overfitting? We need to use data outside the training set. The training set may be, our model may be fitting very well to the training set, but the question is how it's doing outside the training set. And we can do it in two ways. We can use a validation set, so we have some part of our data for training, part for validation, or we can use cross-validation. Cross-validation is very used in other fields of machine learning, and it basically consists in splitting our training set into different folds. For example, here I can split all my training data. These are the points, the red and the blue ones, and I can split into 5. One block here, and so on. And in this case, I train with 4 of the folds, and I validate, I measure the error in the one that was left out. This was not used for training, and it's the set of points used for computing the error. And then I repeat the process, but in the second iteration, I leave out this block, this set of examples, and I train with all the others. And I can do this k times. So if I have k folds, for example 5, I do k folds training, and for each training I use k minus 1 folds for training and the one left out for validation. And then I average everything out, and I have a good estimate of what the error is outside the training set. So I keep doing this for the different folds until I average all of them. Now this is very good when you have when you don't have much data, because you don't need to set aside one set of points for validation. You end up using all of your training set, and it gives you a good estimate of the true error, of the error outside this training set, because you're averaging over the different estimates. However, this is not very used in deep learning, because usually we are doing deep learning when you already have a lot of data, and we don't need to save data by cross-validation. And deep learning models take a long time to train. So if we are doing everything 5 times over just to average out the error, it usually doesn't pay. So typically, even though in machine learning cross-validation in general is very used, in deep learning it's more often that people use train and validation to try to prevent overfitting. So take your training data, leave out some part for testing. We're going to see why right away. But for the part that we're using during training is one part for actually training the network, that's the training set, and another smaller part for validation, so that you keep checking how well your model is performing outside the training data. So this is how we're going to identify overfitting by trying to estimate the true error. So the true error is a theoretical concept, which would be the average error that our trained model will make when we apply it through over all the universe of possible data. Of course, we cannot actually measure that, that's just theoretical, but we can estimate it with some data outside the training set. Now, the problem is with using the validation set for this is that generally we use the validation set to try to optimize some hyperparameters. For example, you can use the validation set to try to optimize the learning rate and see how well it works for giving you those results, or to try to determine when to stop training your network, or to choose what kind of network to use, how many layers, how many neurons per layer, and so on. So if you're using the validation set for this, after a while, your choice is going to be dependent on the error that was given by the validation set. And so this particular value for the error is already quite biased. You already chose things deliberately so that it would minimize this error. This is why we also generally use a test set, which is not used at all during the process of trying to fine-tune the network, train everything, and so on. It's only used at the end to get one estimate of the true error. And this way, it's an unbiased estimate. It may be above or below the true error, but at least it's not biased by any choices that we make. So this would be the general approach. Split your data into train, validation, and test. Leave the test set out. Don't do any choices based on the error on the test set. Use the validation set to fine-tune the kind of model that you're going to use, the hyperparameters and so forth, and also and always use the training set for adjusting the parameters. Then when everything is working fine, you train everything and you get your final classifier, for example, or your trained model, and then you can use the test set to get an estimate of the true error. So this way we can try to select the best model. Not only other hyperparameters, but this would be an example for selecting the best model. This is an example using the problem we saw last week, the miles per gallon problem. So in this case, I trained a network that has a layer of 100 neurons, then 50, 10, and finally 1 neuron with a linear output to predict the miles per gallon value. And this is the error, the mean quadratic error that I get during training. So you see it's end up going very close to zero. But this is the error I get in validation. It's a lot higher than the training error. So this means my model is overfitting. My model is learning things about the training set that do not really generalize outside the training set, because then it starts making larger mistakes on the training set. I could try to tweak a bit the model, and if I use a 30 neuron, 10 neuron, 1 neuron network, I actually get better results on the validation set. So you see here the vertical scale is the same, and even though the training error now is considerably higher, the validation error now is very close to the training error, and it's much lower than what I had before. So it's better to use this 30-10-1 network, even though it doesn't seem to learn as well for the training set, because it doesn't make as many mistakes outside the training set as a fully trained 150-10-1 network that really gets adjusted very well, fits very well the training set, but then doesn't work outside the training set quite as well. So this is how you can do, if you want to fine-tune all of these parameters, you can look at the validation error, and by comparing the validation error with the training error, you can also see if you're overfitting. So basically you're overfitting when you have a training error that is smaller or significantly smaller than the validation error. If things are very similar, then the network is not overfitting. Of course, it can happen if you use a very simple model that both the training and validation error are very large. This means that your network is underfitting. You cannot even learn the useful features about the training set, and that's why you cannot have good results. So by experimenting with different models and looking at these values, you can try to fine-tune things and get a better result at the end. Why does this happen in this way? So let's look at these bias and variance concepts. Bias, just a warning here, it's not in the same sense as we use for the bias weights on the neurons, although it's analogous, but bias here is in the statistical sense of how an estimate on average deviates from the target value. So this would be bias of our model, is how our model is deviating from the expected target predictions, for example. Variance is the dispersion of the predictions around their average. So how widely our predictions vary in our models. And to understand what this means, we would have to imagine that we were training our model on many different data sets. So we have many different instances of our trained model, each one obtained in a different parallel universe where our data set was drawn from the same distribution but was not exactly the same data set. So imagine that we have copies of ourselves in many different universes, and each copy of ourselves is solving a particular problem, but since the data comes randomly, each copy of ourselves has a different data set. So the bias would be we all train the same model in our different data sets, and we get something like this. For example, we have the different data sets over the different universes, and these would be the different models that are trained, but we can see that for one particular target value here in our data, our different models are all predicting around here. So this is the bias, which is the average deviation, quadratic deviation from the actual value. So in this case, our model is biased because it's always overestimating these points here, it's always underestimating these points here, and so on. Variance would be we have these points, we train, for example, a different model. So this is a different model. We got all of these lines over different data sets, and now we can see that the predictions vary very widely in these points. So there is a large variance. The variance is computed like in statistics. There's a very large variance over here. Of course, we don't have different universes to play in, so we don't have these different data sets for our models, but we can actually do this kind of things with bootstrapping or other resampling methods, which we're not going to focus because in deep learning this would not be practical. It's not practical to train a large neural network 500 times just to measure bias or variance or something like this. But this is useful as a theoretical concept because there are two different things we're looking at here. Bias is high when your model is too stiff. So we have points curving here. Our models cannot curve very well, so they tend to be biased, give us predictions that tend towards one end or the other and cannot actually fit the data. So you have large bias and small variance when your model cannot properly fit the data and is too simple, too stiff for that. You have very large variance but small bias if your model can fit the data too well, but even some small differences in the data would lead to a very different solution. So all these different curves use different subsets of the data. Even though the data is always distributed in this S, small changes in which points are used or not make a very big difference to the final result. So a model with high variance tends to fit very well the training data, but then make very large mistakes outside the training data. And this is usually what happens in deep learning. So there is a trade-off between bias and variance. If your model is too stiff, then both the training error and the test error will be high. If your model is too flexible, you can have a very low training error, but then a very big test error here. So usually the error, if you decompose into bias and variance, high bias usually is accompanied with a low variance, and high variance with a low bias. So we don't generally have problems with high bias in deep learning because these are simple models that cannot fit the data, and because the model is too stiff. And so if you're using deep learning, you're not going to find these problems because you already have a network with a very large number of neurons, of weights to adjust. It may be if you try to use a very simple network that you find that your model cannot adjust the data properly, but usually what we do is we calibrate the network so that at least for the training set we can have a very low error. So first we must make sure that our model can adjust, can fit the training set. And this will generally lead us to high variance problems. Our model can adjust the training set, but too much, and it becomes it gives too much importance to irrelevant details, so it cannot generalize. And this is what's common in deep learning. But we can fix this with regularization. Regularization is a change to how the model is trained to reduce this overfitting effect. So to prevent the model from adjusting too much to the data. This way we can reduce variance. It may increase bias a bit, but usually it pays off because we start with models that have very high variance, and if we cut down the variance, we reduce the overall error, the true error of the model. So let's see how we can do this with neural networks. One way of doing this is to add to our loss function a small penalty on as a function of the size of our parameters. So basically we are training the model to reduce the loss function, but also to reduce the size, the magnitude of the different parameters. So it would be in general something like this. This is the loss function, J here. It's a function of our data and our parameters. But the actual function that we want to minimize is the original loss function or the cost function plus a small fraction of a function of our parameters. And there are two usual functions for regularization. L2 regularization or regression is penalizing the square of the parameters. So basically you sum the squared values of all your parameters, and this would be the penalty here. Then you multiply by some weight for the regularization, and this is added to the loss function. L1 regularization penalizes the sum of the absolute values of the parameters. So instead of the square, you use the absolute values. If you use L2 regularization, this is the same as weight decay, because if you put here the sum of the squares of the parameters, then for each parameter, the derivative of the loss function will be the derivative of the original loss function plus 2 times the weight of regularization multiplied by the size of the parameter, because this is simply the derivative of the square here. And so the update rule means that for each time step, you're going to update the weight by taking the previous value of the weight, subtracting the learning rate multiplied by the gradient of your loss function. So this is just gradient descent, but also subtracting this term here. This is the learning rate, epsilon, twice the weight of the regularization factor and the value of your weight. So basically you are shaving a small fraction of the value of your weight at each iteration. And this is why this is called weight decay, because if the weight is not important for the gradient, for going down the gradient, then it tends to decay towards small sizes. You tend to shrink the magnitude of your parameters by using this L2 regularization. If you use L1 regularization, then you actually in this case you're just using the sign of the parameter. So if it's positive, you're going to reduce a bit there. If it's negative, you're going to increase it a bit when you compute the derivative. And this means that some weights will tend towards 0. We'll have a value of 0 because if they are not important for the task that you have your network trying to solve, then they will tend to be shrinked all the way down to zero. So basically, L2 regularization tries to minimize the overall size of your parameters, of your parameter vector. L1 tries to minimize the number of non-zero parameters that you have. So those that are not very useful will end up being zero. This way, even though you have the same model, you can, by calibrating this alpha weight here, so how much weight you give to regularization, you can adjust the learning, the training of the model, so that it doesn't overfit as much. Another way of regularization is by increasing the data set. So the more data you have, the less problems you have with overfitting, because the easier it is to generalize. Of course, we cannot generally just make more data, but in some cases we can actually generate new examples. For example, suppose that you're doing image classification. In some cases you can do translation. For instance, you want a network to identify faces, you can shift the face a bit to the left, a bit to the right, up and down, or if you can do rotations if you want to identify some objects. Sometimes you should not do this. For example, you cannot rotate or flip characters if you want to do character recognition, but probably you can rotate or shift dogs and cats if you want to train your network to identify them in any whatever orientation that you want. Another way of doing data augmentation is by injecting some noise. So again, this is easy to imagine with images. You can imagine that you have a set of images, but you can also change slightly the color values of the pixels, and it will still be the same image. Although now you are creating a set of slightly different images by injecting noise. You can inject noise into the input, you can inject noise into the weights, you can even do that in the output. So in some cases, you may not be entirely sure about the quality of the labels that you have, and so instead of using, for example, 0, 1 labels, you can use something between a very small value and a value close to 1, and this also prevents or tries to help the softmax or the sigmoid output by not requiring it to approach 1 or 0, because that can only be approached by having very large net values inputting into the neuron. So you can do this, you can change slightly these values to improve training. Another thing that we can do is to use early stopping. If we're going to look at the validation error during training, we can see that sometimes the validation error reduces, but then even though training error is going down, the validation error starts going up. So in this case, it's best to train only up to this point and not continue training, because continuing to train at this stage will only lead to overfitting. So early stopping is a very practical way of regularizing our training by controlling when the validation error starts to increase. Another thing that we can do is to reduce variance in machine learning in general, is to average the output of different models. So this is done, for example, in bagging, where we use bootstrapping to obtain replicas of our data set. We train our model over the different replicas, so you get, for example, 100 instances of our model, and then when we want to classify something, we ask for the majority vote between all those 100 instances. So if the model has a very large variance, this works by reducing the variance, usually with very little cost to bias, because we are taking the average response over many different instances of the model. However, this is not practical for deep models, because you don't want to train 100 times your network and then use 100 different networks to classify something. That would be computationally very expensive. But you can do this kind of thing implicitly by using dropout. So with deep neural networks, what you can do is at each mini batch, you turn on or off at random some neurons in your layers. So for each mini batch, you're actually training a subset of your network, so a different network that is being trained inside your own network. And you have many different networks because these are all the combinations of neurons that you can turn on or turn off at each mini batch. So basically, you are implicitly training an ensemble of deep neural networks by using dropout. And dropout is a very useful and very widely used regularization method in deep learning. You can use it with a small percentage, for example, 30%, 20% for the hidden layers. You should not use dropout in the output layer because this is the one where you have your predictions. It doesn't make sense to turn off these neurons, but you can turn off at random neurons in the hidden layers. And then when you go for using your network for classification, all the weights are rescaled by the probability of being on. So if each neuron was turned on 60% of the time, then after training, all its weights are reduced to 60% of their value to take into account that on average that neuron was turned off 40% of the time. You can also do this with inverted dropout, where you, instead of adjusting the weights after training, you increase the activation of the neurons that are left on during training as a function of the probabilities of their being switched off. But basically this is the same idea. So the concern here is that during training, since you are switching off part of the neurons, when you finish training and want to use all the neurons, you need to have some way of rescaling the activations so that you don't overload the responses suddenly. Another way of doing regularization is by adversarial training, because sometimes if you add some input to the network that is really designed to trick the network. So in this case, you have this image, the network identifies as panda with good confidence. This seems like random noise, and actually the network just gives a very small confidence of being a nematode, but this is only 8.2%, so the network is just saying this doesn't look like anything. But this is actually the pixels are chosen to be equal to the sign of the derivative of the loss function with respect to each input here. So they are aimed at where the loss function has its gradient. And if you add a very small percentage of this to the panda, so that even when we look at it, we don't see any difference, because this is we are only adding 7 thousandths of a part of these values to the image, but it's enough for the network to make a mistake and think now that this is a given, because this was actually aimed at the derivative of the loss function there, and so it's a good way of tricking the network and making it shift the class, even though the image seems the same. But we can do this during training, so we can force the network to be more robust here, and by inserting these mistakes that are based on the derivative, on the gradient of the network, we force the network to look for solutions to the parameters where the gradients are not steep, and so it tends to be more robust to small variations in the input. This is another way of doing regularization. So basically, we end up having many different things to choose from. What regularization to use, what architecture to use for our network, the optimizers, and so on. And we need to have some strategies for doing these searches. So one way you can do is manually. You can set up, experiment different things, or you can organize things in a grid. For example, you're going to do different combinations. And this is one of the ways that this kind of problem of selecting all these combinations is solved. You can also do random search. Random search usually works rather well, where you just try a number of networks, and at random you select different learning rates, optimizers, and so on, and try to see then in the end how good things, or what was the best combination. You can do this a bit more sophisticated by using Bayesian search. So you can imagine that choosing the right hyperparameters is itself an optimization problem, and based on the kind of result you have in each example, you can get an estimate of what should be the distributions of new hyperparameters you have to draw from to improve the probability that you'll get a better result later on. So there are increasingly sophisticated strategies for doing this. This is not the focus of this course, so we're not going to talk more about this, but I just wanted to mention this because it can be tricky if you have an important problem to solve. It can be tricky to really squeeze performance out of these models because there are many different options that you can choose from. So in those cases, you can take a look at what strategies can help you select the best combinations. So to sum up, for this first hour, we looked at optimization in a broad sense, not only the selection of optimizers, but then optimizing what model we choose, what regularization parameters, and so on. And the basic message is that you have lots of different options. It's a good idea to understand them and to know how to use them in practice on the toolbox. In Keras and TensorFlow, you have all of these things implemented. And then you need, when you're trying to solve real problems, you need to experiment a bit and try to figure out the best combinations. So you have here some sections on these strategies, on the optimizers, and so on. The textbook goes into a bit more detail than what I cover in the slides. So for evaluation purposes, the slides give you the level of detail that I require, but the textbook can help you understand things a bit better. Okay, so I took more time than I should have. We're going to take a 10 minutes break. Let's start at 15 minutes past 5. Okay, so see you soon.